Good morning. Well, gentlemen, nice to meet you again. It seems that you are arriving at this virtual meeting. So, we will have to talk again about electromagnetics, and we will start where we finished last week, which was three fields that we are able to find out, to solve using the law of the integral law that is common, and we have found that that is a charged ball, a charged wire, and a charged sheet. So this is what we will talk later again, but now we will go on with another thing. So at the beginning I would like to tell you again something which you have already defined in mathematical analysis, and those are differential operators, so-called differential operators. In fact, there are three main differential operators which have big use in physics. That's gradient, divergence, and circulation. So I will try to give you a quick overview of those three operators, of three tools that can describe the law of physics or laws of physics, but I will not do that in the mathematical way that's already done in mathematical analysis 1 or 2, but I will do that more intuitively. So forgive me, it will not possibly be absolutely precise, but I will try to improve your understanding. Possibly you understand it fully now, so then it's in vain, but otherwise I would try to do that. The simplest of those three operators is gradient. Now, when I teach that to Czech students, I talk about downhill skiing. I don't know whether you have a direct experience with downhill skiing. If not, when staying in Czech Republic in winter, that's possible, so try that. So possibly, if that's not downhill skiing, you just won't get downhill from any place. So if you want to get downhill, you would go down. But the down means on a hill that you have certain orientation against the field of height of that hill. And that orientation is exactly opposite the gradient. So if you go in the direction of a gradient, you climb the hill in the steepest possible way. Now, that is something that's quite easily understandable. So gradient is a vector that points to the direction of the steepest, fastest increase of a function. And the size of gradient, the magnitude, is proportional to the speed with which the function rises in that direction. So that's quite simple. I have not drawn any single picture. But now let's think about another operator, and that is divergence. Divergence, well, just imagine that there is a mad scientist who wants to investigate my room. So first, he would like to know whether there is something created in the room, or whether the content of the room is still the same. You know, there was a hypothesis of Fred Hoyle, I think, and that hypothesis quite well described the universe known at, let's say, 80 years ago. And the hypothesis was that in 1 cubic kilometer of a universe, once in a million years, somehow one new proton, or the whole hydrogen atom, appears. Well, somewhere from nothing. And it seems that mathematically it quite describes what is seen in those telescopes. So that scientists, mad scientists, would like to investigate my room. So if he wants to find out whether there is something created, he would have to close the room by a wall. So he would make a tin around the room so that nothing can enter or go out. And of course he would put there a small output. So he would create something like a big tin. So this is a schematic of my room, and he would only put there a small output or input with a meter. And now he would measure the flow of gas out or in the volume. So if the gas flows out, it seems that something is created inside the volume. And he would happily sit down with his logbook and write at 1011 1 cubic millimeter per second, at 1020 7 cubic millimeters per second. And he would have a nice running experiment, and he would say, okay, there somewhere in that room something is created, something happens to be there which was not there at the beginning, and it flows out. But I don't think that he would find out what happens in the room, because the room is rather big and is composed of several different things like papers, tables, myself, chairs, and so on. So he'd possibly like to find out more exactly or more localized information. And that would possibly, so first he would possibly say, okay, I would like to know whether this happens in the upper part or in the lower part of the room. So he would make a break in the room. So now he measures only 1/2 of the room, the bottom part, let's say, but he would soon realize that his logbook, his laboriously obtained logbook full of numbers, is not consistent with this new measurement. Because if there is something, for example, if there would a homogeneous effect that would create the gas in the room, then a half room would produce 1/2 of the amount that produced the whole room. So in order to get something which is meaningful, he would have to get a quantity that is divided by the volume of the measurement instrument. So he would possibly put some quantity like new gas divided by volume of the instrument. If he had a logbook, he would have to divide all the numbers by 2 at this moment, but if he has an Excel file, he would do it quite easily. But now he would possibly like to find out even a smaller volume. So he would again divide that room. So now he has 1/4 of the former room, and he would divide it and divide it so that he would have finally a very small volume in which he would find out the creation of the gas. And Mathematically, if we let the volume to approach zero, we would have a point, a so small volume that it becomes a point. In fact, it gets dimensionless, and that would give us the density of creation of the gas in that point. Remember what we have discussed last week, that small volumes really mathematically approaching zero are physically nonsense. So we understand that this is a volume that is very small, but big enough to cover several molecules. So we would have a limit of delta volume approaching zero, and this we would call divergence. In this case, we call that nu gas. So divergence of the quantity nu gas in the point would be obtained so that we would limit the measurement volume and still record the amount of gas created in that volume. So this is mathematical operator of divergence, which in fact tells us the density of creation of something in a point. Well, we will see soon that creation is a strange word for that, because it's not created from nothing. In physics, it always has a form of a physical law. So, for example, creation, the density of creation of electric field flux is equivalent to charge, which is the law we have seen last time. But now we have creation of new gas, or creation here of Ng, which is the divergence of Ng. We get it this way mathematically. You would possibly find that this is not easy to calculate, just limiting the volume to get smaller and smaller. So we have a special mathematical instrument to calculate this. I would at the moment touch only Cartesian coordinates, x, y, z. Within this Cartesian coordinate system, we could describe that by a special symbolic operator, which we call nabla. This is the nabla operator, and it follows up that nabla is in Cartesian coordinates the partial derivative against x multiplied by unit vector in the x direction plus a partial derivative against y plus partial derivative against z in the direction of z. So it's a vector, it has three components. The x component is the partial derivative against x. The y component is partial derivative against y, and the component in the z direction is the partial derivative against the variable z. So now, using this operator and having a function, a vector function, for example d, we could express the divergence of d as nabla d. Now, this is a product. It's important to understand that Those are two vectors, and there is a dot product. So we have a dot product. So this divergence gets in a vector, the function d, for example, flux density, and the result of that is scalar. In our case, that would be the density of free charge in that point. So now we have obtained a law of physics that is described in a differential way. Now your questions as to divergence, please. If you have no questions as to divergence, I will turn the sheet of paper and start another story, which is about circulation of a vector, which is a bit harder to understand, but is a very powerful device for physics. So remember, we had the nabla operator, we had this divergence formulated using nabla operator. We will return to this sheet a little bit later, and I can try to start with the last operator, which is circulation. Now, circulation is not that important for electrostatics, but when talking about operators, I would do that in one sweep. So let's understand what circulation is. Just imagine that you happen to investigate some field which is not potential one. So a field that is created by circulating. For example, Maelstrom. Maelstrom is a big, or should be in some stories, a big place in the sea where the water is circulating, rotating, and destroying ships. Now imagine that you would decide to investigate this using a special ship which is everything proof, and you would try to get the information about the strange thing which you can't see. There is some water moving and it should somehow affect things, but you should measure it. So how would you do that? So how would you measure circulating? Well, the first idea is that you could measure that, for example, using a big wheel with pedals. So you have a big pedal wheel, like in the first times of steamboats, and you have a big fork, and you insert that wheel into the water, and if there is some circulation around this plane, the water would push to the pedals and make the wheel rotating. So now the wheel, for example, rotates this way. An important comment: the speed at which this pedal wheel would rotate would depend not only on the velocity field of the water, Well, sorry, I interrupt. There is a problem with the video quality at some point. Still, I will put the video on YouTube, like the video from last week, so that you will be able to play it again. But there are no more comments about video quality, so I would continue at the moment. So, the wheel rotates. And just imagine that the water is moving exactly in this plane. Now, if I change the orientation of the wheel, for example, to this position, well, then there would be no force causing rotation of the wheel, and therefore the wheel would not rotate, despite of the fact that the water still circulates there. So my comment is that we have something, the ability of the water rotating in that maelstrom is dependent, the ability to rotate bodies is dependent on the direction. So there is a direction in it, and the way we handle it in physics is that we say, okay, the direction of that ability to rotate is the direction of the bearing of that wheel. So we have this direction, this axis around which the wheel rotates, and this is the direction of the quantity that tells us how able the field is to circulate, to rotate things. Now, having that, we possibly could find out how this force really rotates the wheel. It's quite clear if you have a field like this, so a concentric cylindrical field of velocities, and you put there the wheel to the middle, well, it's quite clear that the wheel would rotate. Which is not so clear at the moment is that if you put the wheel, for example, to here, then the pedals which are down would be subject to water with higher velocity than the pedals upside, which will finally result in circulating or rotating this wheel again, even if it is not in the center of the maelstrom. So it is rotating anyway. So this is something which is important. The ability to rotate objects is contained in every point, not only in the center. Well, now, possibly, if you would we would like to study circulation, you'd possibly not be happy to stay in maelstrom for your whole life. So you would like to bring that experiment to a lab. To do that, you would possibly have a big bowl in which you would, just by stirring, create moving water, and you would possibly need something which is a bit smaller than a pedal wheel. So you would possibly get a very tiny pedal wheel, and in order to get that information from the first experiment and from the second experiment comparable, you would again have to get some density of the ability to turn objects around, to rotate objects. And you could get that by dividing the result by the cross section of the wheel. So if you divide that, you would get the same number if there is a homogeneous rotation at that place. Then the mathematical process would say, okay, and I would get the wheel tiny, more tiny, absolutely tiny, and you would get something which is circulation of a vector, for example, f, which you could express like a vector product of nabla and f. So there is a quantity that tells you how able the field of a function, of a vector function f, is to rotate things. Different fields will be able to rotate or manipulate different objects. So a paddle wheel would be manipulated or rotated by water. Magnetic field would be created or rotated by current and so on. But that's something we would only approach later. So I tried to give you another view of what is circulation. Now, you have an exact definition in your mathematical course. And just to be on the safe side, I would go back. We have formulated the way of notation or determination of circulation of a vector f using nabla operator. We have done the same for divergence using nabla operator. So just we have to note that gradient, which is the simplest operator of a scalar function, for example a, is nabla a, where now the nabla a means that we calculate the partial derivative of a against x, and that is the x component of the result and vice versa. Now this notation works not only in Cartesian coordinate system, but the operator itself is not as simple in different systems like cylindrical or spherical. Your questions, please. Okay. So now we are getting to a point when we will use that instrument to tell something about electromagnetic field. First, we have already established a quantity which is called potential. We have denoted it phi, and that potential is minus integral of the electric field strength along a path, the L, which now, to be exact, needs a dot product and vector symbolics. Well, okay, so we have this definition. Is there anything that would work in the opposite direction? Well, the E, electric field strength, could be also put down like minus gradient phi, which is minus nabla phi. So this is the equivalent of this, just transformed into differential operators. This is integral formulation, this is differential formulation. Now There is another important law. We have an integral notation had last week. An important integral formula. Okay. This has a differential counterpart. Divergence of D, that is nabla D, and that is the density of free charge. Okay. Now what if we combine those two equations? So if we have D, what that would mean to phi. So we have nabla vector product with D, so nabla dot product with D is the density of free charge. Okay, and what if we decide to investigate an area when there is no free charge, a perfect vacuum, for example. So we have, in that case, the situation where nabla dot product with D is 0. Now what if we decide to get somehow to potential phi? Well, first we note that there is an auxiliary Maxwell equation that says that the flux density D is proportional to electric field strength E, and the constant between them, the proportionality constant, is called permittivity. I just note that permittivity of the vacuum is 8.85. I use a computer notation. So it's a very small constant. We have already seen in the Coulomb law. Now, if this is the true, we could say, okay, so nabla applied to the product of epsilon and E, where epsilon, remember we have defined our playground, epsilon is not a function, it's a constant during the fact that we have decided to work with a linear homogeneous media. So we would have which is epsilon nabla E, and this is already known because E is minus nabla phi, so this is rewritable. If E is minus nabla phi, we will get minus epsilon nabla phi is 0. Epsilon nabla phi is 0. I would rewrite that as a new law on the next sheet of paper, because noting that epsilon is not 0, we could write that as nabla phi is 0, and this nabla has a special acronym which is called Laplace. So this is a Laplace operator Laplace applied on phi is 0. This is a Laplace equation, an important equation of electrostatics. Just before we try to talk about it, we should decrypt this triangle, which is the Laplace operator. So Laplace in Cartesian coordinates stands for a sum of second derivative against x plus second derivative against y plus second derivative against z. You apply the Laplace operator on a vector and you receive a scalar. Now this is a Laplace operator and the equation is called Laplace equation. Well, as to Laplace, that was an ingenious French mathematician who has been not only a mathematician but also a physicist. At that time it was quite common, and he has been investigating the universe. He has a special theory of, for example, of the creation of the solar system, and he is known for the Laplace operator mostly at this time. But anyway, he has been living at the time, for example, of Napoleon, who has been first the emperor of France, and